Hey everybody, welcome back to a new video. I just finished this brand new build. This is a 240 volt split phase power cart. Now there are two main components that I purchased for this build. The all-in-one inverter, this is the EG4 6000XP. It's good for 6,000 watts of split phase output. This also allows for 8,000 watts input for solar, and there are two charge controllers. Each one's good for 4,000 watts. To power the inverter, I have this EG4 LL battery. It's their upgraded server rack battery. It's a 48 volt, 100 amp hour battery, good for a little over 5,000 watt hours. Now this entire setup is mounted to a hand truck, so you can easily lift it up and move it around wherever you need to go. And that's probably one of the biggest advantages of a system like this, is that it's completely portable. Now you guys have seen me test a bunch of different power stations on the channel, and you may be wondering, how does this stack up against some of the larger options? Well, one of the most popular options is the Anker Solix F3800, so let's just do a brief comparison. So for the inverter size, these both have 6,000 watt split phase inverters. As for the battery size, the Anker F3800 has a 3.8 kilowatt hour battery, and this DIY option has a 5 kilowatt hour battery. Now what about solar input? That's probably the biggest difference between these two. The F3800 power station allows for 2,400 watts input, but it has a 60 volt cutoff. So you can't go over 60 volts on your solar panels. Now this option here allows for 8,000 watts input, and it goes all the way up to 480 volts open circuit. So you have quite the freedom when using solar panels on this system. Now the cost of each of these is pretty similar. This one on sale is around $2,600, and this one all in is a little bit over $2,700, kind of depending on what you go with. So you can see there's definitely an advantage of going with a DIY system like this. However, I'd say most people are on the fence just because they're not comfortable putting all these pieces together and not knowing what they need to purchase. So in this video, I'm going to go through a brief demo of how everything's connected together and how I built this. And I also have a full parts list down in the video description to give you guys the links to everything you need to purchase to put this thing together. So let's jump into how this is built. Now this build is centered around the 700-pound hand truck from Harbor Freight with the solid rubber wheels. I didn't want to have to deal with pumping up the tires. Now on the back here is a 3/4 inch piece of plywood. It's exactly 4 feet tall and 17.5 inches wide. And basically it just sits down on the bottom of the hand truck, and then I've attached it at 5 points along the back of the plywood using these 3/4 inch pipe straps. Now once I had the plywood secured to the hand truck, I then wanted to mount the inverter. Now there's actually a mounting flange on the top and bottom of the inverter, and there's 6 holes. I decided to use 2 of them here. It's basically just a nut and a bolt that goes through the plywood, super secure. And then there's another flange on the bottom. Now it's pretty hard to see the flange on the bottom of the inverter, but here's one of those bolts that goes through, and then there's another one over here. Now in order to give the battery just a little bit of dampening and to keep it from rubbing on the hand truck, I have installed these 17.5 inch peel and stick rubber strips from Harbor Freight. So I installed one here, and one on the bottom, and I cut off the excess so that it fits the bottom of the hand truck. So the battery will install vertically against these. Now for the power output connection on the inverter, I decided to purchase a 10-foot 240 volt 30 amp extension cable. It's rated for 7,200 watts output. I cut off 3 feet for this end so I can plug in my loads. This is wired directly into the output of the inverter. Now for most use cases, I'm going to take this 240 volt output and connect it directly into my transfer switch. However, if I want to power 120 volt loads, I picked up this adapter where it basically takes both legs and splits it up into 2 sections. So you have 120 volts on this side and then 120 volts on this side. So you can power 120 volt loads if needed. Now the remaining 7 feet of this extension cable I am going to use as an AC charging cable. I have this plugged into the generator inlet, so if solar is not available, I can charge this off a 240 volt gas generator or plug it into one of my larger power stations to charge. So just to clarify, the 6000XP inverter is required to charge from 240 volts if you want to get 240 volts output. They recently put out a firmware update where you can charge this with 120 volts, but it does disable one of the legs, so you only get 120 volts output. Now, I think it's important to clarify that you don't have to use the built-in charging for the 6000XP inverter. If you want to keep the 240 output going, you can use a standalone charger like one of these. For example, this is the EG4 Chargeverter. This one accepts 120 volts or 240 volts input, and it works really well with the gas generator. You can charge your battery up to 5,000 watts. Or you could just use a smaller charger like this. This plugs into a normal 120 volt outlet and charges the battery around 1,000 watts. So there are tons of different options if you go the DIY route. Now, I'll be using solar charging on this probably 99% of the time, but I do have this here as a backup. Now, speaking of solar charging, I have my MC4 pigtails wrapped around the back of the unit so they're out of the way. Now, I'm only using one of the charge controllers. This has two built-in charge controllers. Each one's good for 4,000 watts. So it's around 480 volts open circuit and 17 amps. And I probably won't even get close to that on one of the charge controllers. So I only installed one pigtail, but you could install two pigtails if needed. Now, there are a bunch of videos that go over the wiring, and also in the user manual, it gives you a really good description of what you're supposed to do. But there are not any instructions about the size of these punch outs in the user manual. So I'll tell you that right here. So right here, this one is a 3/4 for the communication. This one's an 1.5 inch for the battery. These three right here are inch punch outs, and then the PV punch out is an 1.25 inch. Now, I did purchase these cable clamps. They basically relieve the stress on the wire. You can go to a hardware store and pick these up, and I just picked them up for the proper size of each of these holes. Now, as for the wire to the battery, I decided to go with 1/0 cable. It is a little bit oversized, but I just wanted to go with slightly larger cable. Now, the terminals to connect up to the battery, these are M8, which are similarly sized to 5/16, but just be aware you have to purchase M8 nuts to tighten these down. Now, as for the output power, this is the first port right here. Now, if you are using 240 volts, you'll have two hots. Black goes in the left one, red goes in the right one. These are your two hots. And then you tie in one of the cables into neutral and one of the cables into the ground bar. For the grid connection, you would use this middle breaker. I am not using that. I am using the generator input. So for the generator input, it's the same. You have one of the hots, which is the black one on the left, the red one on the right, tie into your neutral bar and tie into your ground bar. And you basically just have 4 wires, and they're really easy to connect up. Now, instead of using the 1.25 inch knockout for PV, I decided to use this one right here just because it's smaller and it holds these 2 wires better. But I have my positive and negative solar PV coming in tied into the PV1 terminals. Now, as for the final step, I have installed the communication cable that goes to the 48 volt battery and passed it through this port here. And I've confirmed all of these connections are tightened down and secure as per the instructions in the user manual. So let's go ahead and put the cover on. So I just finished installing the panel, and I thought I'd show you guys a little bit of the cable management underneath the inverter, because now I have a good angle to show you guys. So if you remember, I have the power output over here, and I didn't want this being pulled on so that it was putting additional stress right here. So I added a 1/2 inch pipe clamp here screwed to the plywood so it's supporting the output cable. And I did the same thing on this side for the AC charging cable, so it helps tuck it up away from the battery and also helps relieve stress off this point because I have it skewered here. Okay guys, super exciting step here. I have the battery laying down on the cart, and check out this clearance. It just barely fits. So the final step here is to trim down these 2 conductors for the battery. I have the positive terminal over here, the negative terminal over there. I'm going to cut these down, and then I'm going to crimp on these new 1/4 inch adapters that are compatible with the battery using my hydraulic crimper. Okay guys, we are moving right along. We basically have all the hardware steps completed. Right here you can see we have the communication connected to the CAN port. We have the main positive connected. We also have the main negative connected. Now, the most important part, and probably the trickiest part, is setting up the communication between the inverter and the battery. So let's show you how to set up those communication settings, starting with the battery. So in order to change the communication settings on this battery, first we want to make sure that the circuit breaker is in the off position, and you also have the battery turned off at this switch. The next thing you're going to want to do is look at these dip switches. You're going to want them all turned to the on position or to this direction. So you can see all of them are on. Then what you're going to do is you're going to turn on the battery here. You just wait for it to turn on. Once it turns on, you can press and hold this third button for about 5 seconds, and then it goes into a new menu when you let go. Now in this menu, you'll notice two separate options, the RS485 or the CAN protocol. We are using the CAN protocol, so we're going to go down to that, and then you hit enter on the far side. Now you want to make sure that this is set to Lux. We are using a 6000XP, which is a Lux power inverter, so set it to Lux and then hit enter. And then you have successfully changed the communication setting on the battery. You can exit by pushing this button here. Now once the battery's off, we're going to take this number 1 dip switch and we are going to switch it over. And then we can turn the battery back on and the communication should be saved and ready to connect up to the inverter. So now that we've programmed the battery, we now need to program the inverter, but we need to turn it on first. So we do have the battery turned on. We can go ahead and flip the breaker or power going out of the battery. And then we are going to go to the battery breaker and flip that on. And then we can flip the power switch on the side of the inverter. Okay, you guys can see that the inverter is now powered on, but we need to change the battery settings. You can see it's recognizing it as a lead acid battery. It does show the voltage here, but that's not going to be helpful if we want to be able to communicate. So now you're going to press and hold the enter button for about 3 or 4 seconds, and then it goes into the settings. We're going to push up twice to get to 3. Then we're going to hit enter. And then we have the ability to adjust the battery type. If we push up, we can go to lithium ion. You're going to hit enter one more time. And then we are going to set this to 0 because EG4 is the 0 brand number. So set it to 0, hit enter, and then you'll see that the screen will reset. And then what we'll see is that it's set to lithium ion. You can see the battery voltage. You can also see it's at 99% state of charge, and that it's a 100 amp hour battery. So you know it's communicating to the battery now. One of the final steps on this build was just getting the battery tucked back into the cart. So you can see it's tucked in and it just has barely enough room for all of those wires. Now it is secured to the cart by using a tie down strap. You can see it's attached to that silver handle. It goes around the back. And then looking at the other side, I used the other hook attached onto this handle, and it is super secure on the back. I just have to cut off this excess. Okay, so basically we are finished with the assembly of this cart, and I want to just do some basic tests on this. I have not seen anybody plug an oscilloscope into this to see what the power output is, and I have not seen anybody test the loudness of the fans. Those are probably the two biggest concerns that I have about this unit. It's just how high quality is the power output and how loud are these fans. Now I will say on this build, this is the way that I decided to build it. The options are endless. Now an important aspect of this build is you can use a heated 48 volt battery. There are hardly any power stations out there that are meant for cold charging. There are only two, the AC500 and the EcoFlow Delta Pro Ultra. Those are the only two power stations that I'm aware of that have heated batteries in them. So if you are going to have an off-grid system that's going to be in the cold, you can build this setup and use a 48 volt heated battery, and you can use that all year round. So just a super important aspect of doing a DIY setup. You can build it for your needs. But let's go ahead and take this into my office and do a little bit of testing on the inverter to see what it's like. So what's the process of actually turning on the inverter? Let me walk through that really quickly. So first you're going to turn on your battery. So you're going to push the power button here, and then you're going to flip this breaker on to turn on the battery. Once your battery's on, then you'll flip this battery breaker to provide power to the unit, and you'll flip on the switch on the side over here. Now once that's turned on, you can turn on your load breaker, and then to get the output going to the ports, you'll flip this EPS switch over here that turns on the actual output. Now I have my oscilloscope connected up to the inverter, and check out how clean that sine wave is. Super crisp. There's no distortion in the tops and bottoms. Now, of course, this is not under any load, but we're getting 121 volts output, 60 hertz, and 16.6 milliseconds. So everything looks good there. So let's get a load on this and see what happens to the sine wave. Now, during the next few tests, in order to see what's happening on the inverter, I installed the EG4 monitor app. This does have Wi-Fi connectivity. I'm not a huge fan of this screen, but the app seems to work well. It was kind of a little bit hard to get set up, so I'll include a video that was helpful down in the video description. But right now, it's showing the idle power usage is around 21 watts, which is pretty good. So I've started the test with two 1500 watt heaters, so a 3000 watt load running off the inverter. The fans have kicked up a bit, so let's see how loud they are. So the fans are a little bit louder than a power station. I mean, there are some power stations that are this loud, but just be aware the fans do get up there a little bit, and this is only running at a 50% load. Power output at 3000 watts is looking pretty good. Sine wave's still good, and we're getting 120 volts output. So I've stepped up the load to a little bit higher than 4500 watts, and the fans are a little bit louder, so let's go ahead and test those. So the inverter seems to be handling it just fine. Let's take a closer look at the oscilloscope. Okay, so we're still getting 121 volts output, and the sine wave looks really good. Now I think it's important to mention that because I have only a 100 amp hour battery connected up, I am good for about 100 amps at whatever voltage the battery is. So just to give you an estimate there, if you're at 55 volts times 100, that's 5,500 watts. So you will have to have a battery that's a little bit bigger than this, or that's rated for more power output if you want to get the full 6,000 watts. So that's probably just one downside of this. You're going to be a little bit under the 6,000 watt limit. Now, if you're going to be running an inverter at 6,000 watts continually, you're going to want to have a larger inverter. It is not meant to be able to run at 6,000 watts all the time. Usually what you want to do is you want to size your system for 50% of the output. So if your continual load's around 3,000 watts, buy a 6,000 watt inverter. If your continual load is around 6,000 watts, you're going to want to buy a 12,000 watt inverter. And that will give you the longest life on your inverter. So after those initial tests, you can see that the 6000XP can handle quite the load. We put 4,500 watts on the inverter, and the sine wave output was super clean. And I did test the voltage on each of the phases. They were right around 121 volts, so no complaints there. Now under that load, the fans were quite loud. It's definitely louder than most of the power stations I've tested at 63 decibels. You have a fan intake on this side with a filter, and it pulls all of the air across the front and basically going out through these three fans. So it moves a lot of air, it keeps the components cool, which is the most important part, but it does make a lot of noise doing it. Now, if you guys are interested in more in-depth testing on this inverter, like efficiency testing or surge capacity testing, let me know. Throw a comment down below. This video is just meant to be an overview of how to put everything together and what to buy. And I want to just show a little bit of that performance. But if you guys want a more in-depth video of me testing this out, throw a comment down below. Now, I'll be the first one to admit that this is not a brand new idea. There are a lot of videos on YouTube where people have mounted an all-in-one inverter and a battery to a hand truck for a portable power system. However, most of those systems are 120 volts. And if you're looking for a split phase 240 volt option, the EG4 6000XP is a great option because it's so user-friendly, everything's built into it, and it's completely stackable. For example, you can start off with 6,000 watts output, but you could also stack a second inverter or a third inverter for 12,000 or 18,000 watts output or more. So if you need a larger system, you can start small and get bigger. And it's the same case with the batteries. You can purchase one 5 kilowatt hour battery, and then you can add a second one or a third one or a fourth one, all the way up to a huge system. If you wanted something like 60 kilowatt hours, you could do that because you can connect these together in parallel and feed into the inverters. Now, the other advantage of having a DIY system like this is it's fully customizable. For example, you could take it off the hand truck and mount it to the wall for a bigger system. You could use different batteries. You could use the cheapo Vator 100 amp hour batteries, which are under $1,000, or you can go with a more expensive heated battery, because if you're in a cold climate and the area where this is going to be is not heated, it's important to have that heated capability built into the battery if you want to charge it below freezing. Well, that's basically everything that I wanted to include in this video. Remember, this is just a basic guide of what you need to purchase and what needs to happen to get this thing assembled together. If you guys want a more in-depth video of me testing this or comparing it to maybe a power station, let me know down in the comment section. Now, because this is a guide, check out the video description. I have all the links to the products that you'll need to put this together. So if you're on the fence, hopefully this video is helpful enough to get you to build this project. It's super fun, you can learn a bunch, and it's just something that's super useful for power backup or an off-grid situation. Let me know what you guys think about a build like this or how you would change it. I'd love to get your guys' feedback on that. Anyways, thank you so much for watching. Please smash the thumbs up button if you like this content, and I'll recommend a couple other videos that you guys can check out. Remember, I have my Ask Me Consulting service. I'll have the link to that down in the video description. If you have a direct question about this or any other power station or solar charging, anything like that, reach out and I can definitely help you. Thanks for watching. We'll see you guys in the next one.